Hello, everybody. I'm Manu Bansal. I'm going to talk to you about atomics. This is a joint work with my collaborators, Schulman and Professor Sachin Katti. Before I dive in, let me just point out that a large part of this paper was actually sent in from the delivery room while Aaron was having a kid. So it's really important, so please pay attention. Okay. So I'm going to talk to you about atomics, which is a framework for deploying signal processing applications on wireless infrastructure. So let me start out by making an observation. Many of you probably don't know this, but the LTE base stations that we have deployed today in the infrastructure are actually already built using programmable hardware substrate. These are built using multi-core DSPs, such as the TI 6670 that I show here, and the PHY and MAC layers on these platforms is actually programmed all in software. Right? So that gives us a very valuable opportunity to actually start pushing out applications into the infrastructure incrementally and right away. Right. So we could be deploying a lot of these applications that we have been inventing over the last 5 to 10 years. So for example, using RF localization, using angle of arrival estimation on MIMO arrays, or improving the communication stack using, let's say, video-specific delivery, or sending soft feedback to improve the link adaptation performance. Right. So what is needed in order to deploy these applications on the current infrastructure? So let's start out by looking at a typical signal processing chain that these base stations would be running. It would typically consist of some kind of a data flow graph to describe the signal processing, which is a flow graph assembled using signal processing blocks. So what I show here is an example based out of a Wi-Fi chain, and LTE looks very similar, which includes some kind of synchronization, channel estimation, and bit decoding. Typically, most of the signal processing applications that we have been discussing require one of three kinds of modifications. They either need to tap the signal at the right point in the signal processing chain, or they require to tweak some signal processing block and adapt its functionality, or they would want to insert new blocks or remove existing blocks from the chain. Right? So what we really need from the base station in order to push out these applications is an interface where these kinds of modifications can be made in a modular way, where the programmer can just go and make their specific changes without having to require the underlying signal processing chain and without requiring to touch any other code rather than what they are modifying. Right? But it turns out that providing such a modular interface to these base stations is actually really hard. And the main source of this challenge is the very demanding application requirements for the stacks that these base stations execute today. Right? So let me again base off on Wi-Fi to illustrate what are these application requirements. So what I show here in the gray boxes is a stream of samples that's coming in for a 20 megahertz Wi-Fi channel, which means you have 40 mega samples per second being streamed into your baseband processor, which amounts to about 640 Mbps of constant data that needs to be processed to decode a 54 Mbps channel. Right? And this assumes 16 bits for your samples. And this is a tremendously high computation throughput that the baseband processor must be able to process. So not only must it meet this processing throughput, it must do so in very strict timing requirements. What I show here is an example of a 250 microsecond Wi-Fi frame, which is actually the longest possible frame at the highest data rate. And this frame must be finished decoding in an additional 16 microseconds and no more. Right? So what that really means is that you almost need hardware-like processing performance from your software on these base stations. Right? So how do we get this hardware-like performance today? Typically, it's using a combination of multi-core DSPs, which are customized for this kind of signal processing workload, and by writing very carefully hand-optimized software for these platforms. Right? So let me just walk you through some of the customized features of these hardware boxes that are used to get this hardware-like performance and what they mean for actually the software framework itself. So these processors will typically have multiple DSP cores, which have instruction sets customized for signal processing. And they will also have some hardware accelerators to offload some of the commonly computed tasks, such as Viterbi decoding or FFT. Right? So the programmer can actually leverage all this computational power by parallelizing their code to make use of all these hardware resources. Right? Now, the other difference that we see from traditional architecture is that these platforms will typically expose very low-level interfaces to the memory architecture. As opposed to a typical general-purpose processor, which will have rich cache hierarchy, these processors actually expose the SRAMs at L1 and L2 to the software itself. The programmers leverage this to actually carefully manage placement of data in the memories and therefore tune its effect on the performance of computational performance and the resulting latency, right? Another feature that these platforms typically expose is instead of providing rich cache coherency across multiple cores, they would make available low-level interfaces to carefully orchestrate data movement between different memory regions. Now, why that matters for these kind of applications is because the programmer can actually very carefully tune when data is moved between memories and therefore control the effects on timing and achieve the latency requirements of the protocol. But the flip side is that the burden on the software is now much more than what you would see in an architecture like general purpose processor, right? So all of these low-level complexities, such as manually programming the pipeline or memory management and data transfers, are now pushed into the software. And the effect is that what you end up with is a software system that is very tied to specifics of the hardware, right? So you have kind of compromised the modularity in the process of achieving this hardware-like performance. And as an effect, when you go and try to add your new wireless applications, you can actually end up with very unpredictable effects on timing, even if you're making a very localized chain to your signal processing application, right? So there's an inherent tension between the ability to meet timing requirements and throughput requirements of the application and the modularity of the resulting software system. And that's what we solve in this talk, right? So this talk presents to you a novel abstraction called the atom abstraction, which tries to resolve this tension. So an atom is a unit of execution with fixed and known timing. It's a software module for which can exactly characterize the cycle count every time it executes on this processor. Atom abstraction follows one other property called composability, which says that when you compose two atoms, you result with a new atom, which is to say that the new atom, which is the composition, will have an execution time that is the sum of its individual constituents, right? So maybe you can already start to see why, if you built your software system using only atoms, you would actually have precise characterization of timing of the software system at every level of the system. And if you had atoms being the base, if the atoms were your building blocks, you could actually make point modifications and precisely characterize the effect of timing on, because of that modification. So in the rest of this talk, what I'm going to show you is that you can actually build software base station software using simply atoms and nothing else. All your operations can be encapsulated in atoms. What I'll also show you is that you can still continue to achieve hardware-like performance by building your base station using atoms. And finally, what I'll hope to indicate is that the chain that you result with is modular enough that you can simply insert new applications into it, and you can continue to meet the timing performance of your underlying communication stack. So that's actually the outline of the rest of my talk. But before I dive into explaining how you can build the entire signal processing chain using atoms, let me tease apart the application model of a typical communication stack running on these base stations. So I'll call upon Wi-Fi again to illustrate this. What I show here in the gray boxes is a stream of samples, where samples are arranged typically in the units of data frames. All of these samples must be processed through a data flow graph, which is basically describing the signal processing chain to apply to decode the packets. Right? So this chain that I show here takes in samples as inputs and throws out decoded bits. Now, some of these frames could actually be encoded in different formats, and the signal processing chain must therefore decode each frame in its own respective format. Right? So to summarize, the application model is a data flow graph which can process in multiple modes, and its data flow graph is described over signal processing blocks. And my goal in the rest of this section is to show you that you can actually implement this entire chain using simply atoms. So let's start by looking at how you can implement the signal processing blocks as atoms. right? So let's fall back to our chain, and let me start with the example of the slicer block. The slicer block takes in constellation points and spits out sliced bits. So as we just saw, the slicer block can actually operate in two modes, a BPSK mode and a QPSK mode, right? So obviously the running time depends on which mode it is processing, and to remove this variability, we're going to split it out into two different blocks, one for each mode of processing. Well, at this point, you have fixed what the block is going to execute, but there's still variability possible because of the input size that it will execute every time. So we'll go ahead and fix the data length at the input and output also for each block. In this particular example, I picked 48 complex points, which is the smallest unit that a Wi-Fi chain typically processes, which corresponds to one OFDM symbol worth of data. At this point, the blocks actually run in fixed known amounts of time, right? And they have therefore been implemented as atoms. So by following these two simple rules, splitting out branches and fixing data lengths, you can actually convert all your blocks into atoms. Now that we have converted blocks into atoms, let's see how we can actually assemble a data flow graph also as an atom. But before I go there, let me point out that the principle of splitting out branches applies at the flow graph level as well. The objective is for the flow graph to be implemented so it's an atom, which means it should run fixed set of instructions. But a flow graph that can run in multiple modes cannot be implemented as an atom yet. So you must split it out into its specific modes, right, which will give rise to multiple application level flow graphs. And the principle is the same here to make branches explicit and to split them out. Now, once you have split out your application level flow graph into multiple flow graphs, you can pick any one of those and start to implement it as an atom. So let's do exactly that. Let's pick up the BPSK mode of the flow graph, and let's start to implement it as an atom. So you'll start by implementing all the constituent blocks as atoms, like I described before. And then Atomix provides you an API to declare intermediate FIFOs as data stores to communicate between these atoms. Atomix lets you declare FIFOs by specifying the number of buffers in each FIFO, the data type of the buffer, and the specific memory section in which it should be allocated memory. So it still gives you all the tight control you need in placing your data. Next, you would go ahead and wire these FIFOs to the atoms according to the structure of the flow graph you wish to implement. Now, the point to note here is that there's an additional execution time overhead that you will start to pay in order to access these FIFOs, right? And the question is, will your flow graph still be an atom where you can reason about its execution time? In Atomix, the FIFO access operations are implemented by the system in the form of atoms. So the execution time to access a buffer from a FIFO or to return a buffer is actually fixed and known ahead of time. Depending on how many FIFOs a block wires to, you can precisely calculate the resulting atom computation time for each of these wired atoms. And at that point, your flow graph is wired by the data flow graph, and it is made up entirely out of atoms. And because of composability of atoms, your flow graph itself is an atom at this point. Right? So the principle is the same, which is to explicitly model all costs in the system. And in this particular case, we are modeling access costs of FIFOs as atoms themselves. Now, once you have created a flow graph, let's say you wish to parallelize it to achieve higher computational throughput. So in this particular case, I again refer to the BPSK flow graph, and let's say my objective is to move the BPSK processing slicing part of the flow graph to another core. To do that, I'll move the atom, I'll move the FIFO also, and I'll insert a new FIFO, which would act as a new data source for this atom. Note that all the previous FIFOs are still allocated on core 0, but the new input FIFO is allocated on core 1. By doing this now, I have broken up my flow graph, which I need to reconnect. To do that, I will insert a transfer atom. This transfer atom actually explicitly moves data from the input FIFO to the output FIFO. Atomix provides multiple transfer atoms to move data over either the DMA fabric or through shared memory or through any other mode the platform may expose. By doing this, you have actually completed your flow graph description, now spread on two different cores. And at this point, all you have done is actually inserted a transfer atom for which you precisely know the execution cost. The result is two new atoms which also take fixed known amounts of time to execute. Right? So you could achieve parallelization by following the same principle, that of explicitly modeling any additional costs you might have to incur when you start to parallelize your flow graph. So at this point, we have implemented all our blocks as atoms. We have also implemented our data flow graph in each mode as an atom. But we still need to put in some branches to deal with the decision logic of which specific mode to pick. So I won't go into too many details here, but the basic idea is again the same, which is to explicitly insert a dispatcher atom, which the system provides. And this dispatcher atom can actually read a decision. So in this case, I show the header atom, which can decode the packet header, and then decide which is the next state to execute. And the dispatcher atom can then break the control flow to the appropriate next atom. The point is, we push out all the branches to the top level, and what results is atoms for which you can precisely characterize the timing. So now you can start to analyze the execution time of your final implementation along each path through a state machine that it will take. Details on how you can parallelize state machines are in the paper, which I encourage you to read. So let me just summarize what we did here. Basically, we took the signal processing chain at the application level, and then we implemented in a way that everything was built entirely out of atoms. And remember that the atom is this unit of execution with fixed and known execution time. So at this point, your software is actually modular and has precise timing, which you can analyze even as you make changes. So now that I've conveyed that you can actually build your entire signal processing chain using atoms, let me actually also show you that this can continue to achieve hardware-like performance by using the example of Wi-Fi. So we actually implemented the entire Wi-Fi 54 Mbps receiver, which is standard compliant. And what I show you here is an overview of the allocation that we created using atoms only. So you're taking in complex samples in the units of OFDM symbols and spitting out decoded bits. And what you should note here is that we're able to exploit all the processing power on the platform. Our decoding chain is spread over all 4 DSP cores that were available on the target platform, as well as they're able to make use of all the 4 Viterbi coprocessors to accelerate the performance. So here's our test setup, which I'll use to show you some results. What you see on the left is a sample capture device on the USRPs and a TI baseband processor. Note that all signal processing is running on TI baseband processor, and this is a 6670 platform which is actually already deployed in LTE base stations today. So let me just zoom in on that oscilloscope window, and what you see there are bursts of packet energy and corresponding toggle lines every time we decode a packet. The point I'm trying to convey is that we are actually able to keep up with the line rate of this decoding. And this figure shows you the pipeline structure in practice. So what I'm showing here is the core utilization on all of the 4 DSP cores as this pipeline runs. And you can clearly see the pipeline filling up on core 0 and gradually filling up on other cores. And we could keep up with the line rate with plenty of resources left unutilized. On this plot, I show you actually the ability to meet the latency with very little variance. We varied packet size, and we observed that we could always decode the packet within 37 microseconds, and the variance was as low as 2 microseconds. So you still continue to get the predictable latency that we expected when we designed the system with atoms. So let me also just quickly summarize the development process and our experience with Wi-Fi. What you see in the green boxes here is writing code in Atomix framework, and the red boxes show the resulting code that you would have to write if you didn't use Atomix. Right? So what you see here is that we could do the application with just 3,000 lines of code, an order of magnitude reduction over our estimate of 30,000 lines of code you would have to deal with otherwise. So let me just quickly show you that we could actually easily insert new signal processing applications also in our Wi-Fi chain. So we did 2 case studies, one with the location signature application and one adapting this to long-distance rural Wi-Fi. And in both the cases, we only had to implement few blocks. But what was exciting was that we could insert these applications with as little as 20 or 30 lines of new code. And in doing so, we had actually no effect on the packet decode latency. Our Wi-Fi packets continue to decode as normal. So obviously, this work is based in a set of other works that are related in that they try to design modular frameworks. Some of the examples are modular frameworks for general purpose processors and FPGAs. I'll specifically point out the Ziria programming language, which is a recent work. Our understanding is that Atomics is just the start right now. And you can now start to raise the abstraction level even higher with languages like Ziria, which currently only target GPPs, but apply equally well to DSPs as well. On the other hand, there's the work on real-time operating systems, which try to program real-time abstractions comparable to atoms, but in fact, totally miss the target when it comes to signal processing applications. They do not provide any abstractions where you can implement your blocks and flow graphs as required for a signal processing chain. So to conclude, I presented a new abstraction called the atom and a system called Atomics where you could program your entire application using atoms. And this gives you hardware-like performance, but at the same time gives you modularity to insert new applications. And like I mentioned, I think this is just a start. You can also start to raise the programming abstraction even further by automating some of the scheduling tasks and memory allocation, and start to implement very strong static checks to debug this software. And I think we can also extend this to higher layer processing in the context of network function virtualization, because this is generic framework that lets you program reprogrammable packet processing pipelines. Thanks for your attention. I'm happy to take questions.
Really cool work. So just two questions. I mean, we all know about the click modular router, so why not just create new click elements and call them atoms, right? What's the difference? Right.
So, I mean, I didn't exactly talk about the scale of some of these operations in this work, right? So I'll just point out the quick answer to your question is that there's an order or multiple orders of magnitude difference in the granularity at which click operates and the system operates. So here we are, for example, the FIFO access operation takes 40 cycles to get a buffer and 8 cycles to return it, right? So you're talking of nanoseconds here, and the latencies are on the order of microseconds. And I think the best performance we have kind of achieved with click, or maybe still struggle to achieve with, is on the order of milliseconds. But idea-wise, you're right, they're very similar. Yeah.
And the second question is any of this available, or what's the status of it?
Right, so in the process of releasing this actually, and our hope is that we can actually just give this out with ready-made applications that people like you and me can just immediately start to run on these platforms. So the TI platform is actually available on the market for $600 or so. Some of our software is already out there on GitHub, but I'm not trying to advertise it yet because we still need to release the Wi-Fi application assisting with it. But yes, it's going to be available in a few months.
Awesome, thanks.
Stages that you're branching out to, and they have different latencies. Wouldn't you have to do some scheduling tricks to get the overall latency, to optimize the overall latency? This seems to be reminiscent of some sort of a DAG scheduling problem. So do you do anything specific?
So the idea is that the programmer should be able to precisely analyze what the resulting latency will be. So at this point, we're not automatically scheduling. But you're right, that is the next step, right? So at this point, what you can still do is the control flow model of Atomics is actually just run to completion, right? So depending on how you wired your different flow graphs on multiple cores, you can actually just add up the latencies, including the latency of the transfer atom itself. But yes, the next step is to actually start scheduling this automatically. Then the compiler will be the one analyzing this.
All right, let's thank Manu once again.